Hey everyone, this is Dr. Walker. This is video 209 and it's called Electric Field Lines. We just talked about the electric field and how it's related to electric force and how to find electric field. So now we're going to learn a few more details about the electric field, especially the direction of the electric field. The first thing I wanted to show you is this applet, again by FET, and it's called Charges and Field. It's always nice to just have a little visual. So in this applet, all I'm going to do is I'm going to put a positive charge. It says +1 nanocoulombs. That's a positive charge. I'm just going to put it here in the screen. And then what you see is you see a bunch of arrows pointing away from this charge. These arrows represent the electric field. This particular simulation uses the shading to indicate the strength, so where it's brighter, it indicates a stronger field, and where it's dimmer, it indicates a weaker field. But what I want you to notice is just the direction of the arrows. They're all pointing straight away from the positive charge. Let's go ahead and put a negative charge in here and see what happens. We get the opposites, right? All of the lines that represent the electric field now point toward the negative charge. And let's look at one more thing. Let's go ahead and put a positive charge and then let's put a negative charge next to it. What do you think is going to happen? Let's take a look. Put this negative charge here. Now the arrows are pointing away from the positive charge and they're still pointing toward the negative charge. And so they appear to bend. They used to be going straight out, but now you can see this arrow that was going straight out. It kind of seems like you can make a line and the line is bending toward the negative charge. If you put the negative charge a little bit further away, then you can still see that same pattern. Those lines still kind of appear to be bending away from the positive charge and toward the negative charge. So that's all I want to show you with the applet, just so we can have a little bit of a visual. And let's go back to the lecture. So electric field has a direction, and the direction is in the direction of the force that would be exerted on a small positive test charge placed at that point. So that's a lot to take in, but let's analyze what this is saying. So let's say that we have a positive charge here. Let's completely ignore this negative charge. Completely ignore this negative charge. Okay, if we have a positive charge here, if we put a positive charge nearby, well, we know that two positive charges repel each other, and we know that this positive charge would experience a force away from the other positive charge. This positive charge would also experience a force away from that positive charge. But we're going to consider this big charge to be the source charge. So this is the one that is creating the effect. And this is the one, the test charge here, that is experiencing the effect. So we're not going to look at the effect on the big charge. We're only going to look at the effect on the test charge. So if we put another test charge over here, down below, it would experience a force away from the positive charge. What about over here at point P? If we put the positive test charge here, it would experience a force away from the source, because the source is also positive. So what the statement is saying is that this big charge here, the source here, that is creating an electric field, it's going to point in the same direction as this force that is experienced by this test charge. So even if this test charge was not here, erase this test charge, well, at this point, there is an electric field, I'll call it big E, that is produced by the source, and it points in this direction because that's the direction of the force that the test charge would experience if it was there. So there's an electric field this way. There's an electric field this way, produced by the source charge. And that's exactly what we saw in the simulation, that the electric field pointed away from the positive charge. We can do the same thing with a negative charge now. Ignore this positive charge. If we put a positive test charge right here, we know that opposite charges attract, and that this positive charge would experience a force downward toward that negative charge. Since the force experienced by this test charge is down and to the left here, this means that this charge is producing an electric field in that same exact direction. So using the same logic, we can see that the electric field always points toward a negative charge, and it always points away from a positive charge. Keep in mind that to know the direction of the electric field, we always want to place a positive test charge in that area, because if you were to place a negative test charge here, well, a negative charge would experience a force in the opposite direction, right? Because a negative charge is repelled from a negative charge, and the electric field does not point to the right. So you always have to use a positive test charge to figure out the direction of the electric field. But the easier way to do it is just simply to remember that it always points away from the positive charge and toward the negative charge. So now that we know that, we can use electric field lines to help us visualize these electric field patterns. So this picture shows what we just saw in the previous one, that the electric field points away from the positive charge and it points toward the negative charge. By using these electric field lines, we can figure out a couple more things about the electric field. They give us a little bit more information. So the first thing is, where do electric field lines begin and end? So this looks like what we saw in the simulation. You can here see the electric field lines bending. The electric field lines always begin at the positive charges and they end at the negative charge. If you don't have a negative charge, such as this picture on the right here, then they just extend out forever. And again, this makes sense. If you put a positive test charge here, which way is it going to want to go? It's going to want to go away from that positive charge. The other thing about electric field lines is they can tell us about the strength of the field. The simulation uses shading of the colors with the bright and the dim lines, but that's not typical. Usually you just have solid lines and you can just look at them to see how strong the field is. So see if you can figure out what characteristic of the lines here shows us where there's a strong field and where there's a weak field. Well, if you just pick an area here near this positive charge, you can see how close together the lines are. If you pick an area over here, you can see the lines are very far apart. You only have one here, you have two here, even though this circle was bigger. If you pick, and actually let me just pick a circle that's the same size. If we pick an area over here, right, we can see that there are three lines. So the density of the lines tells us about the strength of the field. Where there is a bigger density, where there are more lines per area or per volume, there's a stronger field. And this makes sense in this picture. We see that the charge on the left is 2Q, the charge on the right is negative Q. So the charge on the left is stronger. There is going to be a stronger field closer to the bigger charge. Just as a quick reminder, the equation for the electric field is KQ over R squared, where Q is whatever charge is producing that field. So remember that the closer you are, right, the smaller the R, the bigger the field. So this agrees with our equation. So the last thing for this video is a question, and it's asking, at which point do we have the strongest electric field? And we are given the lines that are showing the electric field, and these lines are produced by some external source. Where is the field the strongest? So Think about it, pause the video, and the answer is going to be at point A. At point A, you have the biggest density of lines. That means that the field is strongest at that location. All for this video. You now know how to calculate the electric field and how to find its direction. I'll see you in the next video where we will calculate electric fields due to several charges.